All right, grade 11s, atomic combinations. Okay, introducing it. We're going to start off by having a look at covalent bonding, unpacking what it is all about. Okay, what does it involve? And it does involve, of course, the periodic table. Okay, we are going to have a look at Cooper, which we all should remember, and Lewis structures. Okay, on how to draw the valence bonds, or to show how many bonds a certain atom or element makes. Okay, so Lewis and Cooper structures. Okay, if we don't remember those from grade 10, we're going to revise it. Okay, and also on the agenda for today is something called dative covalent. Okay, so it's an extension of this called dative covalent bonding, or coordinate covalent bonds. Okay, that dash shouldn't be there, but I'm not going to take it out now. It doesn't really matter. And also, hopefully today we can have a look at molecular shape. Okay, in my session today, molecular shape of molecules, and which is going to give rise to this acronym, or this abbreviation. Actually, it is an acronym because it's pronounced like a word, called VSEPR. Okay, VSEPR theory or VSEPR model. Okay, and that's all I aim to get through to today. But also in atomic combinations, we're also going to have a look at electron negativity. Okay, we're also going to have a look at electron negativity. So this is my lesson for today, is to get through the covalent and Lewis and Cooper structures, as well as touch on molecular shape. Whatever I don't get through in the session today would obviously carry over to the next session. Definitely looks like electron negativity, which we will cover in the next recording on the next session. But I'm able to at least do 3 out of the 4 things we see on the list today. Okay, so let's start with covalent bonds. Okay, so I'm going to do a lot of explaining, but aim to write down a lot of the keywords that I mention in my talking, or my sharing. Okay, covalent bonds are bonds that are formed by sharing of electrons between atoms. Okay, so they formed, all right, due to the sharing of electrons that takes place between atoms. Okay, so 2 atoms that share, or not, wouldn't say share, but 2 atoms that are coming together, okay, forming a covalent bond. Okay, before we've just known that they bond with each other. Now we're giving an actual name to it. Okay, now to understand this type of bonding, or to understand the type of bond, which is covalent, we need to consider what happens when 2 hydrogen atoms approach each other. Okay, so 2 hydrogen atoms approaching each other to bond. Now, 2 hydrogen atoms are bonded to each other. What do they look like? They look like this, H2. Okay, or in other words, a Cooper structure like that. Okay, which we're all very well familiar with. Okay, we all should remember from grade 10 that each atom consists of an electron. Okay, or each atom consists rather of a single proton in the nucleus with a single electron orbiting it. Okay, we should all remember that. Okay, remember it has 1 electron. It's number 1 on the periodic table, and it has an electron negativity of 2.1 and an atomic mass of 1. And its atomic number is also 1. Hydrogen, we're talking about hydrogen now. Let me just underline it quickly. Okay, hydrogen now. So 1 proton in the nucleus and 1 single electron that is orbiting the atom. As the atom gets closer together, all right, the 2 of them, each electron is attracted to the nuclei of both atoms. So from nucleus to nucleus, all right, 2 electrons are attracted towards the respective nuclei. Effectively, each atom now has a share of both the electrons, okay? Once they are bonded, they share it, okay? Now, of course, we know there's an electrostatic attractive force between the electrons and keeps the nuclei, and the nuclei keeps the atoms held together in a covalent bond, okay? So we must point out that there is an electrostatic attractive force because they bond with each other. If they didn't bond, there will be a repulsive force, okay? An electrostatic attractive force. Between the electrons, and that's why they attract to each other, and that's why the two hydrogen atoms bond. Excellent. Okay. Now, when the forces of attraction are exactly equal to the forces of repulsion, the point of the greatest stability is reached. All right? And this is when the bonding takes place. Okay? When force of attraction, okay, so when attraction, I'm just going to write attraction, but we all know it's force of attraction. Attraction equals force of repulsion. Okay, then we know we have bonding. All the bonding starts to take place. Okay. Now, a piece of general knowledge here that has been pre-calculated for us is that for two hydrogen atoms, okay, the balance of attractive and repulsive force occurs, and the nuclei, in other words, the two separate nucleuses of, or nuclei is actually the plural, but the two separate nucleus of the one hydrogen atom and the nucleus of the other hydrogen atom are separated by a distance of 0,074. Okay, so 0,074 millimeters, okay, is the distance. Let me just put it in brackets. Is the distance between nuclei of the hydrogen atoms, okay? And that, my friends, is equal to what we call bond length, okay? Bond length, okay? Energy is released as the two atoms come together, and then they form the bond, okay? Now, hence, thus, a covalent bond is a shared pair of electrons, as we mentioned at the beginning. Okay, they're thus a shared pair of electrons. Okay, where do these bonds occur? Okay, they occur between non-metals. Okay, hydrogen is a non-metal. They occur between non-metals, right, or between atoms of non-metal elements. Okay, for example, we have chlorine, Cl2, right? We have oxygen, O2, okay? And they also form in compounds, okay? And as well as in compounds, okay? And those compounds, for example, are water. It's a non-metal compound, and NH3, which is ammonia, which is also a non-metal compound, okay? These are all non-metal atoms. Covalent bonds will occur as well as non-metal compounds, okay, such as water and NH3, which is ammonia, okay, water H2O. So just some revision of representation of covalent bonds. Remember that electrons are in the outermost energy level are called valence electrons. Okay, that's the term given to the electrons in the outermost energy level. Okay, because remember the energy levels, or orbitals, s orbitals and p orbitals, etc. In the inner, full energy levels are called core electrons. Okay, so in the inner energy levels, those electrons that are found there are called core electrons. Okay, the number of valence electrons which an element has is equal to the number of the group, okay, but more so, it is equal to the old Roman numeral group number. So of course, Roman numerals went from, in this group over here, 1, 2, and then went on to where we know now as the new group 13 was group 3, 14 was group 4, group 15 was group 5, group 16 was group 6, group 17 was group 7, and group 18 was group 8 under the old Roman numerals. Okay? So for example, helium, or should I say oxygen, is actually in group 16 on the new chart, but under the old Roman numerals it was 6, so that means it has 6 valence electrons. Okay, and nitrogen had 5, carbon had 4, and boron had 3. Okay, except there's an exception here in old group 8, which is new group 18, is that helium, although it's in old Roman numeral group 8, it doesn't have 8 valence electrons, it actually has 2. So helium is an exception. Great, now that we've explained the periodic table and how valence electrons work with the periodic table, alright, valence electrons of any atom can be shown using Lewis structure or Lewis notation. Okay, I like calling Lewis structure and not Lewis notation, but of course I have to teach you both words. Okay, what happens in the exam when they say draw Lewis notation and you used to only saying Lewis structure, so you get used to saying both. Okay, so let's take an example from our periodic table. Let's take chlorine, okay, which we know is represented as Cl on our periodic table, but as a gas, chlorine gas, Cl2. Okay, so we know that chlorine has 7 valence electrons because it is in old group 7. New group 17 is old group 7. Okay, so we draw 7 electrons around it. Okay, so if we have a look at the Lewis notation of chlorine, okay, it will look something like this. So we'll write out chlorine normal, okay, and we'll start drawing. Okay, we use usually X's and dots, all right, with Lewis structure or Lewis notation. I'm going to use X's for this one. So I'm going to fill out 1, 2, 3, 4. Notice that this atom has 4 sides. Okay. Now we do know it has 7 valence electrons, so we've got another 3 more to fill. So then we just fill from the top again, and then at the bottom here, and then at the bottom here, and then we got 2, 4, 6, 7. So this would be the correct Lewis notation of chlorine because it has 7 valence electrons. Okay, so we've done a good job here. If you take example 2, if we take nitrogen, the Lewis structure of nitrogen, okay, it's represented by just the letter N on the periodic table. I'll change color for that. N on the periodic table. We know it is in new group 15, but the Roman numeral for that group was Roman numeral 5. So we know it has 5 valence electrons. So all we do is we just fill out the 4, 1 on each side first, and then we fill in the other 1 for the 5th one. So we've got 2, 3, 4, 5. This would also be correct because it has 5 valence electrons. Okay, if we can remember this little rule and this little trick, we will be able to draw Lewis structure extremely well as understand covalent bonding further. Just to reiterate again, covalent bonds that happen between atoms in molecules can be represented, of course, using the Lewis notation, which we've just done now. And so even though we've used Lewis notation here, we haven't shown the bonding. We've just drawn the Lewis, what's the word I'm looking for? The Lewis notation of one atom in either case. We haven't joined an atom or 2 molecules or 2 atoms yet to each other. Okay. Now, to show the pairing, okay, we are usually, like I mentioned, we use dots and crosses, as I've illustrated in either or. In chlorine, I use crosses, and in nitrogen, I use dots. Okay. When we show that the bond has occurred, we still draw the lone pairs of electrons, okay, which are known as the remaining pairs. We still draw those, okay, which I'll demonstrate in just a moment. We can also use Cooper notation or Cooper structure, okay, and which I'll also demonstrate. So the first example I'll use of bonding two atoms together will be hydrogen, okay. So let's now look at the actual covalent bonding and how we would draw it, okay. Example, again, hydrogen, okay. So the obviously we know H2, which is have two molecules joined to it like that. We have to draw the molecules like in shapes, okay. Cool, it'll look like that, okay. So if we have a look at the Lewis notation, okay, of course now we have two hydrogen atoms, okay. So both of them have one valence electron, so we draw them in 1 and 1. Okay, why have I drawn a dot and a cross if it's the same atom? Well, because I'm showing that one is bonding to another. So I want to show that two different things have bonded to each other, or a bond has occurred. Okay, so when I join them together, the one electron from the one hydrogen atom has bonded to the other electron of the other hydrogen atom, and it will look like that. Okay, as the Lewis structure. Okay, this is the final product or end result of these two. Okay, and then of course we've got the Cooper structure, which is very simple. It's just demonstrated not with dots and crosses, but with a line in between. So like that, which we've all seen before and which I used at the beginning of the session. Okay, cool. So that's the difference between Lewis and Cooper. Okay, so this one seems very interesting, very easy to understand. Let's take another one. Let's take the hydrogen chloride. Okay, write that with a capital H. Hydrogen chloride. Okay, hydrogen chloride, which we know very well as hydrochloric acid, HCl. Okay, let's look at the Lewis structure for it. Okay, the Lewis structure I'm going to draw underneath in this category. I know I've kind of written over it, but the Lewis structure, of course, we know our hydrogen will look like this. Okay, and our chlorine we know has 1, 2, 3, 4, and we're just filling 5. Yeah, 6. There we go. So 2, 4, 6, 7. All right. And now we're going to join them together. So obviously we know there's a space here. Can you see there's a vacant space here for this one to go in? So hydrogen bonding to the chlorine. So there's the X of this X over here showing the chlorine bond, this showing the hydrogen bond, and then write Cl, and then just add in the other remaining lone pairs of electrons. Okay. Under Cooper, of course, it'll just be HCl. Okay, very, very easy. Okay, to explain the hydrogen again, obviously we know hydrogen has a valency of 1. So to attain stability, right, we need stability in every molecule. All right, hydrogen atom must have a pair of electrons. Thus, each hydrogen will share 1 electron when bonding. So we can see this over here is them sharing 1 bond because they each have 1 bond to share with each other. Okay, so we'll call that a bonding pair. Okay, bonding pair. Let's just write that piece of wisdom in there. Okay, with the hydrogen and the chlorine, all right, they both have a valency of 1. Okay, as remember with the periodic table, 1, 2, 3, 4, and then 3, 2, 1. Okay, so they both have a valency of 1. Okay, so just because it has 2, 4, 6, 7 electrons, okay, as you can see, these electron space, or the space sorry, that's a Cl there, is full. There's 2 there, it's full, right? But there's a space there, meaning the valency of 1 meaning for chlorine is that it has a free space for something else to bond to it, but just 1. Okay? So the hydrogen and the chlorine atom, they both will share 1 electron pair. So we can see here by this, just as we see there, there's a sharing of an electron pair right there. Okay? Because chlorine has 7 valence electrons, there are 3 pairs of electrons that the chlorine that do not bond. Okay? And like I mentioned before, these ones are all collectively called lone pairs. Lone pairs of electrons. They do not do any bonding. Only 1 electron in chlorine does the bonding. Hence it has a valency of only 1, yet it has 7 valence electrons or 7 electrons in the outer shell. It's just that the other 3 orbitals are full, right? There's already 2 bonded in them. All right. So that's another example there. I've got a few more examples. Another example would be the methane molecule. Okay, let's have a look at methane, which we know is CH4. Okay, CH4. Okay, let's have a look at Lewis. Okay, and Cooper structure is extremely easy, but we'll have a look at Lewis first, which can become a little more complicated. So obviously we have, let's use orange, we have carbon. All right, carbon is in group 14, old Roman numeral 4. So it has 1, 2, 3, 4 valence electrons. And we know we've got 4 hydrogens that all have 1 valence electrons. Okay, so we have this basically times 4. Okay, but these are the 2 atoms involved. So if we want to bond these together, CH4, okay, let me just put them in there just so that no one's confused. We have 4 of them, okay, they're not bonded to each other. They're all going to want a piece of carbon. So carbon's electrons, I'm writing them like this, and then I'm going to use another color for hydrogen. We'd have X. Okay, we just write over there with X so I can demonstrate the other color. And of course then we'll just write in the hydrogens, showing that a hydrogen is bonded to a carbon. That's why we use dots and crosses to show which bond belongs to which element. We can show that there's a sharing, right? There's a sharing of a bond pair, or a sharing of an electron. They're all sharing, right? The bond pair, okay, or the bonding pair. And then of course we've got Cooper at the end here, which is very simple. These would just all turn into straight lines. So you'd have hydrogen bonded to your carbon like that, and like that. Cooper structure is used a lot in organic chemistry, which is grade 12. I know some schools once upon a time were teaching organic chemistry in grade 11, maybe just as a head start to grade 12. So maybe at the end of your grade 11 syllabus, if you're finished, and some schools may start with organic chemistry, so when you come to grade 12, there's not as much work to go through. There's more time to spend on other things, so you can get through your syllabus quicker and have more time to focus on exams. So I suppose that was the reason why. Alright, so that was methane. Okay, as I mentioned, carbon has a valency of 1, so it needs to share 4 electrons when bonding. Okay, as you can see, it's sharing 4 electrons. Sorry, I think I just, if I play that back sentence back in my head, I think I said carbon has a valency of 1. No, carbon has a valency of 4. Okay, so it has 4 electrons when bonding that it needs to share. Okay, hydrogen has a valency of 1, so it can only share 1 when bonding. Okay, So that means 4 hydrogen atoms are needed to bond with 1 carbon, as we see there, to form the molecule CH4, which is methane. Okay. I've got about a few more, actually. I've got 3 more examples, which we're all going to take. All right. But I think what I'm going to do is maybe just give 1 or 2 as practice before I do the solution. Okay, because I think we all got the theory down. Okay, so for the 4th example, okay, I want ammonia, the ammonia molecule. Okay, so what I want for the ammonia, which is NH3, okay, that's NH3. I would like the Lewis structure, please. Don't bother about the Cooper structure. Lewis structure is most important, right? So the Lewis structure, please, for the ammonia molecule first, and then I'll draw it in after we're done. I'll give about 2 minutes for that. Okay, let's check out the solution for it. Let's pick a different color this time. We just use the plain old. Okay, so remember, of course, we've got nitrogen, which I'll draw over here, which we know has 5. So 1, 2. If you used X's for this, it's not a problem what you chose. Okay, 5 valence electrons. So 2, 3, 4, 5. Okay, I drew it like that because I know how it looks. Okay, by now. And then we've got 3 hydrogens all looking like this. Okay, times by 3 because there's 3 of them. I don't feel like writing all 3 of them. Okay, so for the Lewis notation or Lewis structure, okay, I'm going to draw in my nitrogen first, fill out all its valence electrons. Okay, and then I'm going to add in my 3 hydrogens and show that my 3 hydrogens are sharing a electron. So there are 3 bonding pairs. All right, 3 of them. Lewis notation. Again, please, if you neglect to show these 2 in NH3, you will lose marks or potentially get the entire question wrong. All right, because you have to still show illustrate the lone pairs in the molecule, all right, of the specific atom. Okay. Of course, Cooper structure, we don't do that, okay, because you can't draw a line on top there to demonstrate those 2 lone pairs. So Cooper structure is just NH3 like this, right, which is quite basic. Okay, that's all for Cooper. All right, to look at the next example, that was number 4, so look at number 5. Next example, a very simple one. We have carbon dioxide, CO2. Okay, so again, we're going to start off with the Lewis structure. And then we'll also do the Cooper structure. Valuable marks, of course, in an exam or test. Okay, so obviously we know we have carbon has 4 electrons to share. Okay, this one's a little bit different because now we're going to see the influence of a double bond. Okay, and oxygen has let's just look at the periodic table again. 6 valence electrons, right? 6. Okay, so if we draw the Lewis structure for carbon, it'll just be like this. And the Lewis structure for oxygen, 2, 4, and 6. Okay, and we've got 2 of these. Okay, so the Lewis structure for CO2 would look like this. Okay, you've got your carbon in the middle. Okay, now obviously it's making 2 bonds of carbon are going to bond to 2 bonds of oxygen. So 2 electrons of carbon are going to share with 2 bonds of oxygen. So I need to draw them on the side here. Okay, remember carbon has a valency of 4, meaning it must share 4 electrons when it bonds. Okay, oxygen has a valency of 2, meaning 2 electrons that it can use to bond. Only 2. Alright, so it can only share 2 electrons. The other 4 it can't share because they are lone pairs. Okay, thus for one carbon atom, 2 oxygen atoms are needed. Because carbon's got 4 to share, but oxygen only has 2, therefore it needs 2 oxygens to share 4 of carbon's electrons. Okay, each oxygen will share 2 electrons with the carbon, so 2 bonding pairs will be made. Okay, so there you go, and there we go, and we draw in our oxygen symbols there, and we have to include the lone pairs for oxygen. Otherwise, we will get either the entire thing wrong or lose valuable marks. Okay, now what this is called here, okay, we see them on either side. Okay, they are called a double bond. Okay, that's a P instead of a D, my bad. They are a double bond. Okay, which will illustrate now in the Cooper structure, looks like this. Alright, the double bond. So this would be one arm of the Cooper, that'll be one arm of the Cooper, meaning one bond, one bond, one bond, one bond. Okay, of CO2. Okay, so that's the double bond, meaning that each oxygen shares 2 with the carbon. So there are 2 bonding pairs between carbon and oxygen in carbon dioxide. Of course, there is such a molecule or compound that exists called carbon monoxide, where there's 1 carbon and 1 oxygen, and of course the Lewis structure will be different for that. Of course, we'd only have not 2 bonding pairs, but possibly 1 bonding pair only, leaving just CO. Alright, carbon monoxide, but unfortunately this is carbon dioxide, as we're showing Lewis structure and exactly how it works, as it just is a better representation of it. Okay, I have one more that I'm going to give to everybody. Okay, it's the final one, and this is the nitrogen molecule. Okay, the nitrogen molecule, which is N2. Okay, so I'd like the Lewis structure for it, and then also the Cooper structure for the nitrogen molecule. Okay, we have about 3 minutes for this one because this one's a little bit more tricky. Alright, cool. So this is very interesting about nitrogen. Okay, so if I just draw one nitrogen over here, we know it had a lone pair on top and 1, 2, 3. Okay, now nitrogen has a valency of 3, but it has 5 valence electrons because it is in Roman numeral group 5, or new group 15, old group 5. So it has 5 valence electrons, but it has a valency of 3. In other words, it has 3 electrons that do not have a pair in their energy orbitals. Okay, so this one here, single, single, single. Here we have a double, meaning, let's think of it as a married couple. Couple, no coupling, no coupling, no coupling. If you want to think of it like that to make you understand, please think of it. Okay, you don't need therapy. No one's going to pay for it. Don't worry. You're fine to think like that. Okay, you're fine. Okay, so it has a valency of 3. And nitrogen atom must therefore share 3 electrons with another nitrogen atom. So these 3 here is going to share with a nitrogen atom, which I'm going to denote with its valence electrons with X. Okay, with another one. So 1, 2, 3 is going to share with 3, 2, 1. Okay, so how that's going to look is Lewis notation. So these lone pairs are going to be untouched. So nitrogen and nitrogen are going to keep their lone pairs over here untouched. Okay, some people that draw it tend to draw it over here on the side. It's totally fine. Okay, and here we have electron sharing of 1, electron sharing of 2, and electron sharing of the third one. So it therefore forms a triple bond in the Cooper structure like such. okay, which we see this type of bond in organic chemistry in grade 12 as well. As well as the double bond we saw in carbon dioxide, we see that double bond there as well. So when you see N2 written like this, know that there are 3 bonding pairs of valence electrons that are happening and 2 lone pairs of electrons happening. Where that looks very simple, this looks a bit more complex to show you what's actually happening within the molecule. Now there is such a thing as dative covalent bonds. I'm just going to introduce it here now, but we're not going to divulge it or divulge or dive deeper into it, because we're going to learn more about that in acid and base reactions when we get to that section a little later on in the year. Okay, but it's good that I just mentioned it now, because we'll come back and I'll explain dative covalent bonds under acid and base reaction. Okay, so I'll bring this section in there, sort of like as a revision, and then we'll continue obviously learning acids and bases from there. Okay, so that's what I plan to do. Alright, molecular shape, grade 11s, okay, which also forms part of this atomic combinations section. Okay, molecular shape or molecular structure, okay, it's part of molecular structure, is that with covalent bonding, okay, they are highly directional, okay, almost like a vector in physics, right? Magnitude and direction, okay, here in the shape of a certain chemical or molecule, it's very directional. In other words, it has a direction on it, or it's drawn a certain way, or goes in, maybe it's bent or it's linear, right? So it's very directional. Okay, and or highly directional. Okay, and because it's so directional, it obviously leads to having definite shapes. Okay, and the shape of a molecule will affect the chemical properties. Okay, chemical properties include, which we know from grade 10, melting and boiling points. So the shape of a molecule will affect those 2 chemical properties. Okay, as well as the third one, which is solubility, how well a substance can dissolve. How soluble is it? Okay, can it dissolve in water, which is liquid? The shape of a molecule can be predicted using VSEPR theory. Okay, VSEPR. Okay, it's not spelt, or the letters are not put in the way we say the word, but it does form an acronym though. Okay, we could still say a word, however, it stands for valence shell electron pair repulsion model. Okay, valence shell electron pair repulsion model. Okay, we use this to predict the shape. Okay, excuse me, of a molecule. We use it to predict the shape of a molecule. Okay, what this model assumes, okay, that the electron pairs in the outermost energy level of a central atom are arranged around the atom to minimize the repulsion between them. So, in other words, to increase attraction and minimize repulsion. Okay, let's take, of course, one of the most easiest molecules that exist, and most common molecules that do exist in our society today, the water molecule. Okay, one of the essentials of life, water. All right, H2O. The shape of this molecule is said to be bent or angular. Okay, bent or angular. Now there are a couple of other molecules that also have an angular shape. So I prefer to rather use the first part. I prefer to rather say water is a bent molecule. And we're going to draw it in Lewis structure to show its bentness, okay, so to speak. Okay, so with water, we know we got two hydrogens bonded onto a single oxygen. Okay, single oxygen with two hydrogen bonded onto it. Okay, and excuse me. So two bonding pairs exist, and two lone pairs also exist in the valence shell of oxygen. Okay, and so this is how it would look. We have oxygen, which I'm going to use with the dots, and I'm going to draw single ones over here. Okay, the hydrogens I'm going to use orange. Okay, there we go, and I'm going to write the hydrogens also in orange over here. So it almost looks like, if you must draw it in Lewis, either like this, which shows it's angular, or sometimes we see it like this, which shows quite its bentness. Okay, I prefer that we draw it like this. If we draw it in Lewis, we're drawing it like this to illustrate, of course, its bent. Okay, because we got two hydrogens attached, the bonding pairs of the resultant molecule will have a bent or angular shape. Okay, and that's just, we take it as it is in the textbook because it's teaching us some good things, and we're like, okay, cool, we got to study it. Okay, cool. So water will have a bent or angular shape. Okay, and of course we got hydrogens in it, so we got some hydrogen bonding happening here, which is a very strong bond, and hence pulls the molecule to look like we see it over there. All right. The next shape that exists under this valence shell electron pair repulsion model, which is VSEPR theory or VSEPR model, is linear. Okay, now there's about two molecules that back up the linear shape. Okay, I'm going to start with a simple one first, which is carbon dioxide, CO2. We remember from our Cooper structure. Okay, I'm just going to draw Cooper structure like that to eliminate some time. Okay, the carbon dioxide molecule is known as a linear molecule as well. Although there are four bonding pairs, all right, in the valence shell of carbon, because of the double bonds, okay, these will be in two groups. As we see here, there are two groups of bonding pairs. Okay, so there's four bonding pairs, but two groups of it, two on either side of carbon. Okay, so in mathematical terms, we see that these will move 180 degrees from each other. And the reason why they do that is to minimize repulsion. Okay, the two oxygen atoms are attached to these groups of bonding electrons, and thus the molecule is linear, which we can evidently see from the Cooper structure. With the Lewis structure, however, we know we have the existence of these. Okay, there, and let's not forget the lone pairs of oxygen, which do exist over here. But we can see the molecule, even when it's drawn out in Lewis structure, it is very much linear. Okay, very much linear shape. Okay, so let's write in brackets over here, linear. Number one. Okay, still the second example is of a linear molecule under VSEPR theory would be, I'm going to write this one out in full, beryllium chloride. Beryllium chloride, which is known as BeCl2. This is also a linear molecule. Okay, now if we draw it out in Lewis structure, which I'm going to do in just a moment, I'm just going to change the color quickly. We've got the beryllium atom in the middle. Okay, and I'm going to use X for it. Then we're going to use the dot for the chlorine. And we fill in the lone pairs. So 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. All right, and the 7th one there, sharing one. There's a shared pair there, and there's a shared electron there. Okay, 2 bonding pairs. Okay, the simplest example of this repulsion, okay, occurs in the beryllium chloride molecule as we see on our screens. Okay, beryllium only has 2 pairs of electrons around it, so it only has 2 pairs to share. Okay, to minimize the repulsion between these electron pairs, they are arranged so that they are given opposite sides of the beryllium atom. As we can see, we have two chlorines opposite each other around the beryllium atom. Okay, as we can see similarly here with the carbon dioxide molecule as well, it is drawn in a linear shape, meaning that the molecule is indeed linear. Okay, so those two molecules have what is known as a linear shape. There are other shapes, of course. Okay, we've explained the bent or angular, and we've also explained the linear. There is still another 3 more. Okay, so to continue with those, third one is what I want to use an example of boron fluoride. Okay, let's say my spelling fluoride correctly. Yes, I am. Boron fluoride molecule, which is BF3. So 3 fluorines bonded to 1 boron. Okay, and this shape is known as trigonal. Yes, planar. This is known as trigonal planar. Okay, and this is how it's drawn in Lewis structure. Okay, so we have 3 outer boron. Just give me one moment, guys. Hold on a second. So 3 from the periodic table, it had a valency of 3 valence electrons, and fluorine only has is in group 7, so there's 7 valence electrons also around it. So we would it has 1 pair to share. All right, so it'll share it like this. We draw it underneath there, and then we'd add our fluorines in here on top and on the side. Sorry, let's just get rid of this one. It's not a real one. Okay, and then we'll draw in the other lone pairs of fluorine, which is also 6 lone pairs. Okay, there we go, and there we go. Okay, so this idea, we can predict the shape of the boron fluoride molecule as trigonal planar, which looks, if I must just draw it out, looks like this. Okay, I know I didn't use straight lines, but it looks like trigonal, like a triangle. Okay, because it has 3 pairs of electrons around it for boron. Okay, so this would result in a flat molecule just for boron itself, with the fluorine atoms arranged at about 120 degrees around the boron atom. Okay, and this would be called trigonal planar. Each triangle, of course, in a I think it's isosceles triangle, I stand corrected. All right, each angle here would be 120 degrees. All right, because all sides are equal. The same thing here as we in this molecule for trigonal planar, the boron fluoride molecule. Okay, there is one that has 4, okay, and there is one that is more pyramidal, okay, but there is one that has 4, of course, and that would be methane. Okay, the methane molecule. Okay, the methane molecule, which you know is CH4. This shape is called tetrahedral. Okay, tetrahedral. Okay, and we know how it looks. So I'm not going to really draw it out really, because we know how methane looks. I've drawn it before. Okay, basically, if I had to draw the Lewis structure, the diagram is only two-dimensional, so we cannot show the three-dimensional tetrahedral arrangement, okay? But we still draw the electron pairs as far from each other as possible, right, when we do draw the Lewis structure, okay? But basically, of course, what we already know is there are 4 bonding pairs of electrons in the valence energy level of carbon. For these 4 pairs to be as far from each other as possible, they would move into a tetrahedral arrangement around the carbon nucleus. Okay, so I can't show it right now because I don't have a 3D model, but usually those 3D atom models at school, if the school does have them, you'll be able to play around with it like that. Okay, each bonding pair has a hydrogen attached, and thus the molecule becomes tetrahedral in shape. Okay, and if you a quick Google search will pull up the 3D model of methane, which is tetrahedral. The final one, number 5, if we take ammonia, the ammonia molecule, all right, which we know is NH3, this is the shape, or the molecule has a shape called pyramidal. Okay, because there are 3 bonding pairs and 1 lone pair in the valence energy level of the nitrogen atom. Okay, we see there are 3 bonding pairs and 1 lone pair. That's the lone pair, that's the 3 bonding pairs over here, meaning they are free to join with another atom. So these 4 pairs of electrons would move into a tetrahedral arrangement, because tetrahedral means 4. Okay, around the nitrogen nucleus, of course, but this time, since there are only 3 bonding pairs, right, there are only 3 bonding pairs, all right, or 3 bonding pairs with as a result of 3 hydrogens that are attached, okay, then this molecule will be regarded as pyramidal, okay, because of the joining of 3 hydrogens as we see over here. So this molecule is known as pyramidal. Okay, so again, I can't demonstrate the 3D-ness of it, so you can see that there is a pyramid. Okay, but NH3 ammonia would be said to be pyramidal. Tetrahedral usually means 4. So if you see hydrogen with 4 hydrogens in it, we can assume that it could be most likely tetrahedral, and when we see 3 hydrogens in it, we could assume that it's most likely pyramidal, but we'd have to judge based on the molecule. And that wraps up my session for today on what I wanted to cover. I managed to cover at least 3 out of the 4, and next week we hit the ground running with electron negativity, grade 11. So awesome. Thank you so much for joining me once again. Have a good one. Until next time.